And you've probably heard about quantum computing and all of its woo-woo, voodoo magic ways of computing, and it's going to crack all of your encryption and find all the secrets and all of that stuff and yada, yada, yada. I'll be pulling on that thread. But let's just start with this one, a light introduction into it. Quantum code breaking, you'd get further with an 8-bit computer, an abacus, and a dog. Computer scientist Peter Gutmann tells the Reg why it's a bullet. The U.S. National Institute for Standards and Technology has been pushing for the development of post-quantum cryptographic algorithms since 2016. If large-scale quantum computers are ever built, they will be able to break many of the public key crypto systems currently in use. Peter Gutmann, a professor of computer science at the University of Auckland, New Zealand, thinks PQC is bollocks, nonsense for our American readers, and said as much in a 2024 presentation, Why Quantum Cryptanalysis is Bollocks. And here is the presentation. Thank you for whoever. Hang on. It's Boyle. It's Boyle Ox. Okay, laugh. It's Boyle Bollocks. Boyle Ox. Bull. I don't know. Shut up, Laughly. Shut it, okay? Okay, your Bollocks is Bollocks. Gutmann's argument is simple. To this day, quantum computers, which he regards as physics experiments rather than pending products, haven't managed to factor any number greater than 21 without cheating. So there's two elements here. One, there are no real-world products that any consumer can get their hands on in terms of quantum computing. So where is the benefit so far? All of these things are experimental. And just like AI, they require a huge belief in the end goal outcome of them. And they require a bunch of money, a bunch of energy being directed to it, and a bunch of hardware capabilities to make them happen, even in just a purely experimental setting. And then what? Then what do you get out of that? Well, just like AI, you're not getting much, are you? The current quantum computers can only factor a number greater than 21, but they have to cheat to do it. Quantum computers and PQC are both enormously complex. Both the common process for cracking RSA public key encryption is relatively straightforward. But the common process for cracking RSA public key encryption is relatively straightforward. In other words, there's a difference here in that RSA encryption cracking is a straightforward thing, but then you have these complex systems to do something straightforward. So then you have to factor in some mathematical equations here. If you know about some of the NP times Q, mathematics that are used to get you to a particular, prime number, things like this, then you can see how this plays out. He breaks it down. So he provides an example where N is 21, P could be 3, Q could be 7 for a not very secure 5-bit RSA implementation. When N is 10, 24, or 2048, finding two prime numbers requires a tremendous amount of computational power. And so he kind of describes the differentiation there. Now, the claim is that quantum computers are going to be able to essentially find a very quick path to what are the prime numbers that get you to a key that unlocks the encryption. That's the claim. The claim is that these quantum computers are going to be able to go like, and then they find the right key. And so the right key would be, these factorial numbers to get you to, whatever prime you need, right? And so encryption essentially would just be a thing of the past because all current encryption methods would just, they'd be instantly crackable in a moment. Some engineers, apparently the claim is, some engineers claim quantum code cracking could be a thing within 2 decades. So they're saying everybody has to start preparing for this. However, when these systems were used to compute a factor to the number of 21, it failed. The algorithm worked 14% of the time due to rampant qubit errors. And then this leads into a thing called D-Wave. And D-Wave has these special computers that apparently are finely tuned. Does this sound familiar to anyone? They are finely tuned to do better on these kinds of problems. However, I can't remember his name already. I've already forgotten his name. Peter Gutman says these are all tricks. Everything that they're using to get you to these results are all tricks. Quantum factorization is performed using sleight of hand numbers that have been selected to make them very easy to factorize using a physics experiment and, by extension, a VIC-20, an 8-bit computer, an abacus, and a dog. Does this sound familiar at all? Kind of like the training data or the software, or the benchmarks that these LLMs are being trained against or used to provide, some kind of metric, like look at how well these things run. All they're doing is sleight of hand tactics, but with quantum computers as well. And as the article continues, Peter essentially makes the case that this is all hand wavy, too little, too late. Everybody's kind of locked into this path and they can't find a way out. So they have to hope that if they throw more money and more hardware and more effort into this path, that they're going to get to the point of quantum computing. There's another problem with this, though, and we're going to get into, at least one of those problems, including more. So this bold area kind of touches on further problems that we're going to cover in future articles. Contrary to popular claims, quantum algorithms don't try all solutions at once. Instead, they carefully manipulate qubits to amplify the probability of measuring a useful answer at the output while suppressing the probability of measuring any other answer. It's roughly similar to a magician's card trick. Rather than checking every card in the deck for the one that was chosen, the magician uses a clever sequence of steps to make the chosen card more likely to appear without actually knowing what it is. Compared to classical algorithms, quantum algorithms can more effectively scale with problem size. This means that for a sufficiently large problem, they may be able to compute an answer more efficiently in time, energy, or cost than classical alternatives. For smaller problems, it is likely that classical computers will retain a clear comparative advantage for the foreseeable future due to the overheads in quantum computing. So I hope that makes sense to everyone. I thought it was pretty clear. Essentially, the quantum systems that are being used for computing solutions is just a way to statistically determine what would be the most likely path to the most correct answer, and then exclude the least likely ones. You can already see a problem with that, though, right here from the get-go. What if it statistically, through the probabilities determines that the least likely path ends up actually being the correct path? And then there are other problems that are inherent to these quantum computing systems, which we'll continue digging into down the road. So there you go. I thought this was a good one as an introduction into the quantum computing thread, because I feel like it has a very big overlap with the AI stuff we talk about these days.